Hi there, and welcome to the release video for the April release in 2026. My name is Christian Humbert, and as usual, I'm very proud to present the latest features in our binary level analyzers, AIT StackAnalyzer, TimeWeaver, ValueAnalyzer, and TimingProfiler. As with every release, there's a whole range of new features. I've picked out a few highlights for you and can't wait to show them in this video. Let's dive in it. The first improvement is to our DWARF reader and processor. We have enhanced C++ template demangling for specific compilers. We've improved the export of type information so that you can now output all available type defs, and many more improvements. For the full details, please check out the release notes on our website. But let me take this here video as an opportunity to quickly remind you on where to find the DWARF debug info in our tool and what you can do with it. Well, here I have a small C++ example task that I've run through StackAnalyzer. For this demo, the only thing you need to know is that this main function here declares three local pointers, OPTR, MPTR, and BPTR, right? Of different types, namely of other base, multi, and the base class. You'll see in a moment that there's kind of type hierarchy here. The multi-class has been derived from either the base or the other base class. So we are dealing with multiple inheritance here in this example. But don't worry about the details for now. What we can also see here in this example is that we have calls to virtual functions. For examples, we're calling the opfunc2 function here on the object that MPTR points to, and the opfunction1 on the same object, but this time through OPTR, right? And using the DWARF debug info, all our analyzers can automatically determine the correct function candidates for these virtual functions. So in this case, the multi, opfunc2, and the other base opfunc1 candidates. You see they are nicely demangled here in the C++ style. You can also see that on the call graph level. Now let me quickly remind you on where exactly in the tool you can access and work with the DWARF debug info in more detail. And that's through the information symbols view. You just need to click to extract symbols, and in the upper part of that view you'll find the DWARF info nicely visualized. Here, for example, we can inspect the class definitions of the multi-class, for instance here, the base class, or the other base, right? When I click here, I see it inlined even. You see there are, for instance, in the base class, we have some virtual functions, virtual members. What you also can see is that, well, what you can visualize is the inheritance graph of these classes. So let's click on that here and say show inheritance graph, and the DWARF view nicely shows you the inheritance situation. So here you can realize that multi has been derived either from the base or the other base class. And this DWARF extraction and processing has been now extended and improved so that it works also with much more other compilers than before. The next new feature is about the XML report, specifically the WCET path output in that report. You'll find now even more details in that path output, and I'd like to give you a quick look at that. I have here a very small timing profiling analysis of a RISC-V binary test application, which basically consists of a main routine that implements a function pointer call And this function pointer call has not been resolved yet. As an effect, you see this external unresolved target routine in our call graph. But you can also see that the call of it here is part of the worst case path, right? Well, now in previous versions of the analyzers, in the XML report output, which you can find, by the way, when you go to the to the analysis items output here and open the XML, then you find the WCET path output here under estimate analysis task, then the WCET analysis subsection, and here is the WCET path. And you can see here already, you can see the entry, which is the routine with the index D1, R2. The indices are defined somewhere above. And this corresponds to our main function, actually. And you see already two more routines, namely the routine D1, R2, the main routine, and now also this external routine node which got the index R38. No? If you unfold here our main function, you see there are at some point there is this call instruction, computed call instruction that here targeted or calls the target routine D1R38, which is our not yet resolved but external routine node that you can find here as well, right? So here you obviously don't see anything more because it's an external routine. Yeah. Okay, this has been improved in this new version. The next point concerns TimeWeaver analysis only. Here we have now added a new warning for cases where certain trace snippets cannot be mapped onto the reconstructed call and control flow graph. Well, this can be an indicator, for instance, that something in the analysis is still misconfigured. If, for instance, some plugs or code snippets were reached during the trace recording, but were marked as infeasible and unreachable in the analysis, right? Let me give you a quick demo on that. In this demo example, I have our 5 millisecond task from the scenarios product example. And as you know, there are these two different execution scenarios of the 5 millisecond task depending on the outside signal. If the signal was, true, then the math index was assigned with 10. If it was false, the outside signal, then the index was 20. And in the consequence, either the BS function or the math function was called. So in our traced scenarios, obviously, as you can see here by the tau info, we have like 150 scenarios or executions of the same 5 millisecond task where we assigned the index with 20, means that we have to enter the math branch. And in 593 scenarios or snippets, that's the number of snippets, the index was set to 10, and in the consequence, the call went via BS, right? By the way, the worst case path was determined here independently going over the math function, because this at the end leads to a higher WCET bound. Now, assume that we, maybe by accident or intended, indicated this branch here infeasible. Namely, let's annotate the call instruction here. Let me go here, program point, go to the as file. Well, we can make it maybe a bit more symbolic. So we could say, let's take the first call to math and turn that into infeasible, right? Okay, in the consequence, this branch should become infeasible. And let's see first, yeah. And the other routine BS should be taken for the worst case now. Yeah? So the analyzer was forced to skip that worst case path, and in the consequence, the only other alternative was going over BS. But Remember, we had this 150, I guess, was it, snippets that went over the math branch, right? And now in this new version, you get a nice warning now that, well, the analyzer skipped some trace snippets because they could no longer be mapped to the graph. And this is exactly the situation here. The analysis says, okay, this branch is marked as infeasible, but in these 150 trace snippets, we took exactly that branch, right? And so this is kind of a contradiction, and therefore this now causes very prominent warning. And well, if you say, okay, I know what I'm doing, and this infeasible is correct in my configuration, then you can, of course, like with any other warning, but please locally for that corresponding 5 millisecond BS math routine only, suppress that message with this number 17423, right? And then this warning will again vanish. Yeah? But please do that with care and yeah, only if you know what you're doing. Now let's enter the section on new annotations in this release. The first new is a new functor, which allows to check for the existence of symbols, instructions, routines, or loops. This can nicely be used within some if annotation scopes, for instance, and also as an alternative to the try directive. Let me show you how this works. I've loaded our scenarios example again, and we are here in the 5 millisecond task. You remember from the last demo. Now imagine we would like to turn the entire math subgraph into infeasible, and we want to do that in the global AS file. If we go there and say routine math infeasible globally, right, and rerun, for instance, the 5 millisecond task, well, then we should see an effect. Well, this has worked out and no warning was issued, but in any other task that does not contain the math routine, like this one here, sorry, let's see. Yeah, you will get an unable to resolve program point math to valid routine. You know how to solve this problem by typically provide a try directive here. Then the annotation will only be applied if the specified routine is reachable in the present analysis. So you see the warning will vanish here when we rerun. Now with this release, we introduce an alternative to the try and move it to the if scope in annotations. You remember we have an outer if scoping where we could, for instance, now say if some routine math exists, then apply the infeasibility annotation. So this should have the very same effect. If we go to the 5 millisecond task, it should be applied. Let me reload. Yes. And when we rerun the 1 millisecond task, it also does not cause any issue. No? Okay. And yeah, you can see that, or you can use within the exists functor. You can check for existing routines, for symbols, for loops, and even individual instructions. Some of you requested a feature in the ICE annotation language to implement a typecast of objects in the binary. And we have now introduced that in the April release. Let me give you a demo. Assume you analyze a program containing an array, here a bigger array with 100 elements that is used as kind of a heap that has been pre-allocated where objects of different type are placed during the execution. Assume further that we place an unnamed object here to the very beginning of that heap structure, of that heap array, of type record. For instance, where is it here? This type record is a structure type consisting of different components, in especially the integer component here at offset 8. Okay, now if you want to annotate the content of that object of type record inside of this A heap, you can now do that in an AIS annotation. Here, let's take the example here. I've prepared it already. You can say, okay, I'd like to assign the value 4 to the object that begins in my A structure, in my A array, but I'd like to cast that here to the type of record so that I can access the subcomponent int comp. And if we do so and run the analysis now, we can go to the report file and nicely see here in the section of the constant data that at exactly the address D00010 plus offset 8, so let's go back by now, the A starts here at this 10, and at offset 8 in our record type, we have the int comp, we now store our value of 4 as the first byte. So you see this is only possible with this cast functor that we can apply to our A array. This concludes the presentation of the latest features in the April release. As usual, this was just a small subset of all the changes. If you want to have a closer and more detailed look, please go to our website. And yeah, thank you very much for your interest. See you next time. Bye bye.